Welcome back everyone to MAU 170. This is lecture 8 in week number 4. Last time we saw the concept of stability for linear systems. We saw that either a system is stable when the poles of its transfer function lies entirely on the left-hand side of the S-plane, or in other words, the real parts of the poles are all negative. If this doesn't happen, the system is not stable. However, if the poles lie at most on the imaginary axis, then the system is marginally stable, given that the multiplicity of such poles is at most 1. If that is not the case, the system is unstable. We also said that in case we cannot compute directly the poles in order to check the real parts, well, there's another available criterion to check the stability of linear systems, and that is the Routh-Hurwitz criterion. So let's repeat it here. The Routh-Hurwitz criterion says that a necessary and sufficient condition for system stability is that there are no sign changes in the coefficients of the Routh array. So today, we'll learn how to construct this Routh array in order to check the sign of the coefficients. It all starts from looking at the characteristic equations. So the characteristic equations, as we saw last time, can be written as usual as an equation with a polynomial equation with coefficients that are real. And the first thing to check is the sign or the signs of these coefficients. Again, this is not the Routh-Hurwitz criterion, but this is something that you can check beforehand before constructing the Routh-Hurwitz array. Because if this first condition is not met, then you don't have to build the array. And so you already know that the system is not stable. What is this first thing to check is that all the coefficients of the characteristic polynomial must have the same sign. So either all positive or all negative. Once you've checked that, now we're ready to build the Routh array. So the first thing that we want to do, we want to construct a table, and this is done in the following manner. So we start by writing down the powers of S vertically. So we start with S to the power of n, then we write downwards S to the power of n minus 1, S to the power of n minus 2, all the way to S squared, S and S0 or constant coefficient. And then we're gonna fill the first two rows using the coefficients of the characteristic polynomial. And we're gonna place them in this order. We start from the first entry to the left, to the top left. So we're gonna write an here, and then we proceed this way. We go down first, an minus 1, and then we go up again, and then down again until we fill everything. So we follow this pattern here. Down, diagonally up, down, diagonally up, down, until you finish all the coefficients. So you'll see that you have an equal number of coefficients on the first and the second row if n is odd. Instead, if n is even, then you'd have, well, you would still fill up the first two rows in the same way, but you will be left with one empty spot. So we would start with an, then an minus 1, then diagonally up an minus 2, an minus 3. But then you'll finish right here, always following the same pattern: down, diagonally up, down, diagonally up, down. So A0 would be on the first row. So if you don't have anything, if you have an empty entry, well, that is also equal to 0. So you can just leave it empty or substitute it with 0. This is a general rule. So the first step, very simple. You take the coefficients of the polynomial, the characteristic polynomial, so an minus 1, all the way to A0, and you construct the first two rows of this matrix or this table. Now it's time to fill the rest of the table. And so let's go to step 2 and let's see how this is done. So once we've written down the coefficients on the first row, and here I'm considering this case here in which n is even. So we have an evenly distributed first two rows. Now what we want to find first is this element over here. So first column, third row. So what we're going to do is we consider the terms of the first column right above the spot that we want to compute. So for the first two columns above, that is an and an minus 1. And then we pair them with the other two coefficients to the right of them. And so we have this 4 coefficients here. So these 4 coefficients will be used in order to find the value in the red box. So how do we do that? So we start from an minus 1, and we follow an 8-figure pattern, or a figure 8 pattern, I should say. So we go an minus 1 times an minus 2, and then we go minus an times an minus 3, everything divided by an minus 1. So you see that we sort of have an 8 here. So let's write it down in the proper formula. But again, if you remember the figure 8, it's going to be easier. So we start with an minus 1 times an minus 2 minus an times an minus 3, everything divided by an minus 1. And so we've found the value for this term here in the first column. All right, now let's move on. Once we have also this value here, now the next one to be computed is this light blue box. So third row, second column. So we still need 4 coefficients, and we apply always the figure 8 formula. But now the way the coefficients are picked, you always pick coefficients from the 2 rows above. So you always want the first 2 to belong to the first column, and then to the column to the right of the box that we're interested in. Since now it's the blue box, we want these 2 coefficients here. And now what we do, we just stretch the figure 8, but we proceed in the same way. So we have an minus 1 times an minus 4 minus an times an minus 5, everything divided by, once again, an minus 1. So you see that it's still an 8, but now it's more stretched. So we can write it down once again. And this is just a sort of a mnemonic algorithm. There's nothing really to think about. It's just you have to learn, and once you do 2 or 3 problems, you're gonna master it. So we have, starting from an minus 1 times an minus 4 minus an times an minus 5 divided by an minus 1. All right, so then what you want to do is you complete in the same fashion the other or the remaining terms of the third row, and then you start with the following row, that is the fourth row. So in this case, we have this purple circle, and we use the same tactic, always the figure 8, always considering 4 coefficients belonging to the 2 rows above, always considering the first column and then the column to the right of the element that we want to compute. So in this case, it's going to be the second column. And so we repeat the figure 8, this times this minus this times this divided by this. All right, so in other words, we have red box times an minus 3 minus an minus 1 times blue box divided by a red box. And you see the pattern here. So you can complete the whole table like so until you find all the coefficients of the first column. And this is important because the first column constitutes the actual Routh array. That's what we want to check. And so you just take a look at the coefficients or the signs of these coefficients, and if they all have the same sign, then the system is stable. If not, the system is not stable. Let's take a look at an actual example and things will clear out, hopefully. So let's consider this characteristic equation. We have s cubed plus s squared plus 2s plus 24. So here I'm already giving you the characteristic equations. If you don't have it directly, well, remember that the characteristic equation is the denominator of the transfer function of a system. Well, and this is actually, sorry, I should say the characteristic polynomial. Characteristic equation is when you equate it to 0. Anyway, the characteristic polynomial then is the denominator of the system transfer function. Okay. All right, so let's start by taking a look. This is not 25, but it's 2 times s. So this characteristic polynomial is of degree 3. Before starting computing the Routh array, let's check that all the coefficients of the characteristic polynomial have the same sign. So here we have 1, 1, 2, and 24. They're all positive, so we can proceed. The necessary condition for stability is met. We don't have a necessary and sufficient, and thus we need to find the Routh array. All right, so we start here with s cubed, s squared, s, and s to the power of 0. Now we fill the first 2 rows using the coefficients of the characteristic polynomials. So we start with the coefficient of s cubed, and then we go down using the coefficient of s squared, and then diagonally up using the coefficient of s, so it is 2, and then down again, that is 24, and that's it. We don't need, we don't have any other coefficients, so we've completed filling the first 2 rows. Now we want to find the first column, third row element. So using the figure 8 approach, we have 1 times 2 minus 1 times 24, everything divided by 1. So 1 times 2 minus 1 times 24 divided by 1. And so we have 2 minus 22, sorry, minus 24 divided by 1, and this is minus 22. So we can write it down here. All right, what about the element over here? But remember that we need always the first, or the first 2 terms are always of the first column, and then the other 2 terms, to apply the figure 8, are to the right of the, with respect to the column of the element we want to compute. But in this case, this is just an empty column that has 0 and 0. So when you have an empty column, well, this element is simply 0. And if you don't trust me, we can do it step by step first. So here we would have 1 times 0 minus 1 times 0 divided by 1. So you'll simply have 0. So if you want to compute an element that refers to a column with both zeros, then the element itself is 0. Now let's go ahead and complete the Routh array. This is quite straightforward. Now we only need one last element, the last element of the Routh array, that is column 1, row 4. So as usual, we take, for the figure 8, the 2 elements of the first column of the 2 rows above the element that we want to find, and then the 2 terms to the column to the right. So we have this 1, 24, minus 22, and 0. All right, so now you can either repeat the figure 8, or whenever you have a 0 to the bottom right, the value for the coefficient that you want to find is equal exactly to the top right. So to whatever it's above the 0. So we're going to have here 24, and I'll show you why using the figure 8. So this is just to speed up your calculations. So here we would have, using the figure 8 technique, minus 22 times 24 minus 1 times 0, everything divided by minus 22. You see that here we are subtracting 0, so we have minus 22 times 24 divided by minus 22, which leads to 24. So once again, if you have a box and the bottom right corner, or the bottom right element is 0, then the result of this computation is simply the value above it, so 24. All right, so now we don't really need this element right here, which anyway would be 0, because we would consider these two elements and these two elements being the second column all zeros, then this element would also be 0. But we don't really need it because we have all the Routh array formed. We have all the coefficients, so we're ready to assess the stability of the system. Let's check the signs of these coefficients. We have 1, 1, so positive, and now we have minus 22, so one sign change, and then we have plus 24, so another sign change. So we have 2 sign changes, and I said it last time, but let me repeat it this time too. Every time you have a sign change in the Routh array, that represents one pole in the right-hand side of the complex plane. So we have 2 right-hand poles. So in other words, 2 poles with positive real part. And so obviously this implies that the system is unstable. You can actually check the poles. You can compute the poles directly to, well, to verify whether your stability assessment is correct or not. So we can compute the poles of the system directly, and you'll find that P1 is equal to minus 3, and P2 and 3 are equal to plus 1, plus or minus I square root of 7. You see that although P1 is or has a negative real part, both P2 and P3 have positive real parts. And so both P2 and P3 are on the right-hand side of the complex plane, as predicted here. So the Routh-Hurwitz criterion tells you how many poles are on the right half plane, but it doesn't tell you where exactly they are. Otherwise, you know, if you already knew that, the Routh-Hurwitz criterion would be kind of useless. All right, let's move on considering another example. Now let's take this characteristic polynomial. Now it's a 4th order one, so we're increasing the complexity. We have s to the power of 4 plus 2s cubed plus 3s squared plus 10s plus 8. So first thing here, I'm going to go a little bit faster. First thing that we want to do, we want to complete the first two rows using the coefficients of the characteristic polynomial. So we start by 1, then we go down, then diagonally up, down, diagonally up. And here you see that we've finished with the coefficients, so we have an empty spot and we can just replace it with 0. Now let's start computing this green box element. So we're referring to these 4 coefficients. So the green box is going to be 2 times 3 minus 1 times 10 divided by 2. So we have 6 minus 10, which is minus 4, divided by 2 is minus 2. All right, so you see already here that we have a minus 2 as a coefficient in the Routh array. So if the question had been, oh, is the system stable? Well, you already know that the system is not stable because there's already a sign change in the Routh array. However, if I'm asking you to tell me how many poles are on the right-hand side of the complex plane, well, then you have to compute all the coefficients of the Routh array. And here for exercise, we'll just do that. All right, so now we need to compute this term. So now the 4 elements that we need are these 2 and these 2. Now, pay attention. We have a 0 on the bottom right corner, so the result will just be the value above it, so just 8. We don't really need to do the whole calculation. And now we're ready to go and compute the next element of the Routh array. Oops. Okay, so now the coefficients that we need are going to be these 4. And so we have that this is always using the figure 8 trick, minus 2 times 10 minus 2 times 8, everything divided by minus 2. So here we have minus 20 minus 16 divided by minus 2. So we have minus 36 divided by minus 2. We have plus 18. What about the element to the right of it? Well, the element to the right of it would use these 2 coefficients and these 2 coefficients, which are 0. So we simply have 0. So now we're left with the last entry for the Routh array. So let's point out which coefficients we need to use. Well, the first column of the 2 rows above, and then the other 2 terms of the column to the right of it. Once again, here we have a 0 at the right bottom corner. So the result, the coefficient we're looking for is simply the one above. And so we have 8. All right. Once again, here we have the Routh array, first column of this table. 1, 2, minus 2, 18, and 8. There are 2 sign changes from 2 to minus 2 and from minus 2 to plus 18. And so we have 2 right-hand poles. And so we have an unstable system. Once again, if we were able to compute directly the poles, we would see that 1 would be equal to minus 2, then another one equal to minus 1, so on and so forth. So good. And the remaining 2, P3 and P4, are equal to plus 1/2 plus or minus I square root of 15 over 2. So you see that the real part of P3 and P4 is positive. Therefore, the system is unstable. Okay, so everything good, right? Yes, but there are a couple of special cases. So what happens if we have a 0 as an element of the Roth array? Because the criterion says that we want the coefficients of the Roth array to have all the same sign, but 0 doesn't really have a sign. So if we happen to have a 0, then we need to take some measures to deal with it. So the first case would be that you'll find 1 0 in the Roth array, and then all the other some of the other coefficients, I should say, or at least one of the other coefficients on the same row are different than 0. Let's take a look at an example to see what I mean. So here we have a 5th order characteristic polynomial. So let's construct the table, filling in the coefficients 1, 2, 2, 4, 11, and 10. Now let's start finding the first column, 3rd row coefficient. So we have 2 times 2 minus 1 times 4 divided by 2. And so we have 4 minus 4, which is 0. All right, so here, when you find a 0, the bell should go off. And now you have to pay attention to the remaining terms in the same row. So let's find the coefficient to the right of it. Now the terms that, or the coefficients that we should consider are these 4. So we have 2 times 11 minus 1 times 10 divided by 2. And so we have 22 minus 10, 12 divided by 2, 6. All right, so we have a non-zero element in the same row. So we are in case number 1. Case number 2 would be simply when all the elements of a row are equal to 0. So this special case that I named with first or 1 really refers to when we have a 0 in the first column, but then non-zero elements in the other columns for a specific row. So now the trick is we'll substitute 0 with epsilon usually referring to a very small number. So we're going to have a number that tends to 0, okay? So what we're going to do, we just substitute that 0 with epsilon, and then we'll proceed as usual. So instead of having 0, we'll just write epsilon, and then everything as was earlier, so 6, and obviously the other term was 0. And now we can proceed as nothing happened. So let's say we want this term here, which coefficients should we consider? These 2 and these 2. So this term is going to be equal to epsilon times 4 minus 2 times 6 divided by epsilon. And so we have 4 epsilon minus 12 divided by epsilon. So 4 epsilon minus 12 divided by epsilon. All right, then let's move on to this coefficient. So now we can compute it using these two and these two. All right, here we have a 0. So what we're looking for is the one above, that is 10. And then we're ready to jump to the next row. All right, right here. So we need these 4 coefficients here. And so this is equal to, here it gets a little bit more complicated because now we have 4 epsilon minus 12 divided by epsilon times 6 minus epsilon times 10 divided by 4 epsilon minus 12 divided by epsilon. So here we can multiply everything by epsilon. So we have 24 epsilon minus 72 minus 10 epsilon squared divided by 4 epsilon minus 12. And so for now, I'll just refer it to this box with an arrow. And finally, we need the last entry of the Routh array. So now the terms that we need to consider are these 4 here. Fortunately, here being a 0, what we're looking for is simply 10. All right, so now we have the elements of the Routh array. And let me highlight them. Here we go. There are 1, 2, epsilon, 4 epsilon minus 12 divided by epsilon. And then this 24 epsilon minus 72 minus 10 epsilon squared divided by 4 epsilon minus 12 and 10. All right, now we have to take a look at the sign of these coefficients. It's obviously not straightforward. So what we have to do is we have to take, remember, epsilon is a very small number that technically should be 0, but we're going to take the limit of the coefficients with epsilon in it for epsilon that goes to 0. So what is the limit of this coefficient? Well, this is simply minus infinity. So it doesn't really matter that we have infinity. All we need to know is that we have a minus sign. So we already have a sign change. So we know that the system is going to be unstable. But let's take a look whether the system is, how many poles on the right-hand side of the complex plane we have. So let's also take the limit for epsilon that goes to 0 of the other coefficient. That is 24 epsilon minus 72 minus 10 epsilon squared divided by 4 epsilon minus 12. One thing that I should say is that we consider epsilon, well, I wrote it here. It's a small but positive number. So technically, epsilon tends to 0 plus. So in this case, you see that, this goes away. So you have plus 6. So this very long coefficient was nothing but plus 6. So the Routh array actually becomes 1, 2, 0 plus. So we'll consider it as a positive sign. Minus infinity, 6 and 10. So once again, we have one sign change going from 0 plus to minus infinity, another sign change from minus infinity to plus 6. Two sign changes two poles on the right-hand side, unstable system. Once more, we can directly compute the poles just to verify that our assessment in terms of stability is correct. We have P1 that is negative real number. P2 and 3 are complex conjugate with negative real parts. But P4 and 5 are also complex conjugate, but now their real parts are positive. And that's exactly what we predicted. These are the two infamous poles that corresponds to those two sign changes. Let's take a look at another example. In this example, we're going to have a characteristic polynomial with a parameter in it. We have k. So we might have some values for k for which the system is stable, and other values for k for which the system is unstable. That's usually what happens. If you have a parameter, then depending on the value of this parameter, well, the system might change its stability. Or we might find out that for all values of k, the system is stable, or for all values of k, the system is unstable. We don't know that a priori, so that's why we need to build the Routh array. All right, let's start with filling up the first two rows. So it's going to be 1, 1, 1, 1, and k. And obviously we have a missing one, so we can just replace it with 0. Well, first of all, before starting here, I'm just going to say that k is going to be different than 0. But if k was negative, then the system is obviously unstable because we don't meet the necessary condition for stability. Remember that the necessary condition for stability said that all the coefficients of the characteristic polynomial must have the same sign. So if k is negative, obviously it doesn't have the same sign as the coefficients of which are 1, 1, 1, and 1, positive ones. So we already know that for k that is negative, the system is unstable. But for positive k, we might still have some ranges. Let's say if k is from 0 to 10, the system might be stable, and then from k greater than 10, the system might be once again unstable. We don't know that yet. So let's construct the Routh array. So starting from this term of these 4 coefficients, this is pretty easy to see that we have 1 minus 1 divided by 1, so we have 0. Let's replace it right away with epsilon. Oh, well, before doing that, let's check that the other elements of the same row are not all 0. So now we want to find this coefficient. Therefore, we need these 2 and these 2. It's great. Here we have a 0 at the bottom right corner. So what we're looking for is above it, that is k. K, we said that is different than 0. So what we can do is replace the 0 with the epsilon. We're still in the special case number 1. Okay, now let's proceed with the completing the Routh array. Here we have epsilon times 1 minus 1 times k divided by epsilon, or 1 minus k over epsilon. And then here we have 0. And then finally, the last entry of the Routh array. since we need these four coefficients, we have a 0 right here. So what we're looking for is the value above. And once again, that is K. All right, so our Roth array is 1, 1, epsilon, 1 minus K over epsilon, and K. Well, we said that epsilon is we take it as a positive number, so 0 plus, but we need to find the sign of 1 minus K over epsilon. For epsilon that tends to 0 plus. Well, this is equal to plus infinity if K is negative, and it is equal to minus infinity if K is positive. So actually, the system is always unstable no matter what the sign of K, because if K is positive, then we have 1, 1, 0 plus, minus infinity, and a number that is positive, just K. So we have two sign changes, two poles on the right-hand side of the complex plane. System is unstable, but if K is negative, and we already know that this must be unstable as well, but let's check. We still have 1, 1, 0 plus, and now we have plus infinity, so no sign changes so far. But now we have K that is negative, so we have 1 sign change. So although we only have one pole on the right-hand side of the complex plane, and since we only have one, this must be real, the system is still unstable. So we can draw the conclusion that the system is unstable no matter the value of K, or for all K's minus 0, because we've excluded that. Why did we exclude K equals 0? Because otherwise we would have a row full of zeros and we don't really know how to tackle that case. But we'll learn how to do it right now. So that is the second special case. That's when we have a row full of zeros. And let's see how to treat this case by taking a look at an example. Before even starting this example, I already tell you that if you find a row full of zeros, then the system cannot be asymptotically stable. That's as easy as that. It can be either marginally stable or unstable. There's no asymptotic stability associated with that. So as soon as you find a row full of zeros, then you can already say that the system is not asymptotically stable, but it might be marginally stable. So we need to know how to proceed. So let's see how to tackle this case. So as usual, we build up our Roth array like we don't know what's going on. So here we have 1, 2, 4, 8 in the usual pattern. So let's find the first term here. That's 2 times 4 minus 1 by 8 times 8 divided by 2. So it's 8 minus 8 divided by 2, simply 0. And then the other term, well, we would need 1, 2, or to use, I should say 1, 2, and another column full of zeros. So this other term is also 0. So in this case, we have a row full of zeros. So how do we tackle this case? Well, step one is we need to select a so-called auxiliary polynomial by taking a look at the row right above the row full of zeros. So in this case, we have this row over here. And the auxiliary polynomial, we're going to call it A of S, A as in auxiliary. So how do we build it? We use the coefficients of this row. So you see that this row refers to S squared. So the first coefficient is 2. So we're going to write 2S squared. And then we skip odd powers of S. Or in other words, it should be plus 0 times S. And then we use the other coefficient. In this case, it's 8. So you can simply write 2S squared plus 8. And it'll turn out that every time that you find a row of 0, that always is in correspondence to an odd power of S. Therefore, the auxiliary polynomial being above that always refers to a row with an even power of S. So the auxiliary polynomial in this case is 2S squared plus 8. Step 2, just take the derivative of such polynomial with respect to S. This should be very easy because it's just a derivative of a polynomial with respect to S. So derivative of 2S squared is 4S. And then derivative of 8 is simply 0. And now we use the coefficients of this derivative, which is still a polynomial. It's 4S is a polynomial itself. And we replace the row full of zeros with the coefficients of such polynomial. Now, notice that we have 4S and we want to replace the coefficients of S. And so we have 4, and then we don't have anything else, so we simply have 0. And that's it. Then you can just complete the Routh array. And in this case, we have the final element that we're looking for is, well, it uses these 4 coefficients. So we have a 0 right here. So what we're looking for is simply an 8. All right, so here the Routh array tells us that we have 1, 2, 4, and 8. No sign change. So technically the system, you would say the system is stable. But in the beginning, I told you that when we have a row full of zeros, we cannot have a stable system. So if you find that all the coefficients of the Routh array are positive once you've used this trick of the auxiliary polynomial, taking the derivative and substitute the 0 row with the coefficients of the derivative of the auxiliary polynomial, then this means that the system, if you find that all the coefficients have the same sign, the system is marginally stable. So we just say that it's not unstable. And in fact, if you calculated the poles, then you would have that P1 is equal to -2, and P2 and 3 are plus and minus 2i. So if we place them on the S-plane, one is here, and then the other 2 are here and here. So they are on these 2 are on the imaginary axis with multiplicity equal 1. Therefore, the system is marginally stable. So it's not properly stable in the asymptotic sense, It still contains the word stable. So, you know, some could say, oh, well, it's still stable, but for the definition that I gave you, this is not really stability, but it's just neutral or marginal stability. A couple of things that I want to point out and that you can use as useful information is that the auxiliary polynomial A of S contains some poles of the characteristic polynomial. In other words, you can factorize the characteristic polynomial using the auxiliary polynomial. So A of S is just a factor of delta of S. So the other factor is going to be another polynomial, B of S. And this is useful because A of S is obviously of a reduced order with respect to delta of S. So if you can already have a factor, you can find the sum of the poles of the transfer function. And let's take a look at that. If we take a look at the the auxiliary polynomial, 2s squared plus 8, then the roots of this equation, so this is s squared plus 4 equals 0. We have s equals to plus or minus 2i, which are exactly P2 and 3. So we already have two poles. In the beginning, if you were just to start from the third order system, so with the third degree polynomial, well, you wouldn't be able to spot right away two of the roots. It's not easy, you know. We don't really have well, we technically could do it for a third order even by hand, but it's usually kind of difficult to find them. So using this property, that is, the auxiliary polynomial contains poles or roots of the characteristic equation, we can find information about the system. Comment 2. Well, I've already said that. It's that the row full of 0 is always associated with an odd power of s, or s to the power of 2k plus 1. So for instance, s to the power of 1, s cubed, s to the power of 5, so on and so forth. And so the auxiliary polynomial is always a polynomial of even order, because it's one reduced once you take once you go up from the row of zeros. Once you go up, if this is, let's say, s to the power of 3, you're considering s to the power of 2. So it's always an even order. So it can be 2, 4, 6, 8, so on and so forth. All right, comment 3, and I've already told you that a system with all zeros in one row can only be either marginally stable or unstable. And this is because all the possible configurations that we can have of the poles, the poles, well, not only are they symmetric with respect to the real axis, and that happens all the time, but for this specific case, for the special case, we also have a symmetry with respect to the imaginary axis. So let's say, for instance, that if we had a pole here for the system, then if we find out that we have a row full of zeros in the Routh table, then we must have also a pole that is symmetric to this one with respect to the imaginary axis. And so in this configuration, well, you see that this pole has a positive real part, so the system is unstable. Another configuration that we might have is having two poles on the imaginary axis. This configuration is symmetric with respect to both axes. And so the system in this case is marginally stable because these two poles are on the imaginary axis. However, if we have the same poles but repeated twice or more than twice, well, the system is unstable because the multiplicity is greater than 1. But again, the symmetry is kept. And finally, we can have a couple of complex conjugate to the left, but of course, we have to maintain the symmetry with the imaginary axis. And let me repeat, this symmetry with the imaginary axis is not always required, but only if we find that a row is full of zeros. So even in this case, configuration 4, the system is unstable, having poles in the right-hand side of the plane. In order to factorize the characteristic polynomial, as I said, you should apply the polynomial division. So since we have the polynomial, auxiliary polynomial that is equal to 2s squared plus 8, well, this is also equivalent to s squared plus 4 because it has the same roots. So what you can do is apply the polynomial division. So here you write the polynomial you want to divide, which was the characteristic one. Oops. And if you don't remember how to divide polynomials, you start from this term and you divide it by the first term of the divisor. So it's s cubed divided by s. So it's simply s. And now you proceed by multiplying s by both of these terms. So you have s cubed and then 4s. And then you subtract these two. So you have 2s squared plus 8. And then you repeat that. So once again, you take 2s squared divided by s squared. And so this gives you 2. So we have s plus 2. And now you take 2 times s squared and 2 times 4. So 2s squared and plus 8. You subtract these two and you find that you have no remainder. And that's what you need to find. So it means that s plus 2 is the polynomial that we called b of s. This was our characteristic polynomial. This is b of s, and we divided it by the auxiliary polynomial. So for what I wrote in comment 1, we have that delta of s being equal to a of s times b of s. We have it, all factor out. So you can also factor it even more. And now you can recognize the 3 poles that we've listed before. We have P1 equals -2, corresponding to this, and P2 and 3 equals to plus or minus 2i, corresponding to these two. All right. Then here I have another example. I'll leave it to you to take a look. It's just a little bit longer. Don't worry about the division between polynomials. It's better that you refresh it, but it's not really necessary. I don't really care if you know how to do it or not. You'll see that for this system, you also have that is marginally stable. But I want to go on to another example that is more of a design example. It's obviously semi-serious, as you can tell from the figure. So let's say that we have a laser gun and we want to point it to this apple, sort of like the I think it was late 80s or early 90s movie, Honey, I Shrunk the Kids or something like that. The dad had this sort of laser gun and wanted to shrink objects. So he was trying it with an apple. And well, anyway, so we want to point exactly the laser towards the apple. So what we can do is we can control the pitching angle of this gun. So our control variable is going to be the pitch angle, theta. And so let's say that you have a joystick that drives the motor in the gimbal to control the pitch angle of the ray, and you are the controller because you actually operate the joystick. All right, let's put some numbers and some functions into this. So let's say that you run some tests and you'll determine the transfer function of the system, of the plant, that is of your, this is the plant and this is the fruit. But no, the plant is the laser ray with the actuator, with the joystick. And so let's say that you determine that G of S is equal to 1 over S plus 1 times S plus 2 times S plus 3 times S plus 4. And clearly we have that the poles of G of S are -1, -2, -3, -4. Here I wrote it already factorized, so it's easy to see where the poles are. You see that all these poles are real and negative. Therefore, your system is stable. So there's no risk of you changing or applying some input to the joystick and having the laser ray just going madly one way or another. It will still stabilize to a certain angle eventually. It might wiggle a little bit if the system is underdamped. Let's say it might oscillate a little bit before pointing in the right direction. That's not exactly what you want for this application. So therefore, you might want an overdamped system. That is, let's say that you are in this configuration and then you give it an input so that it points this way and you want it slowly to reach this angle. You don't want an overshoot, in other words, and then going back and then forth until it settles. So you see here also the application of the concept of underdamped versus overdamped systems. All right, anyway, this is just an open loop control, because you have the input in your whatever movement of your hand on the joystick, and then you have an output as in the pitch angle of the laser gun. So once again, here we can also visualize the poles in the S plane, -1, -2, -3, -4. Everything good. Now, let's say that you don't really trust yourself and you're not sure, you cannot really control the joystick. It's a little bit the response, even let's say you move it a little bit and then the laser gun moves a lot. And so you don't really trust your capabilities of controlling the laser gun using the joystick. So why don't we add an automatic feedback control? Well, that would be the sensible thing to do. So what we would do is to add a sensor that can measure the angle, the pitch angle, connected to a computer, and then the computer will function as the controller. So it will send a signal to the joystick, and it'll be able to give it the right input based on the actual position of the actual angular position. And that's exactly the concept of feedback control. So here we have our plant, we have transfer function for our sensor, and then we have a controller. So we need also a control transfer function. Now let's make things a little bit easy. First of all, let's assume that we have a perfect sensor. So h of s is equal to 1. And then we also assume that the controller is just a proportional controller. A proportional because it's proportional to the error. So the controller itself is just a constant, and we're going to call it k. And remember, this is also known as gain or simple gain. And with k, that is a positive number. So being k a constant, you'll see that, remember, the signal after the junction was the error. So the control input, it's going to be k times e of s. That's why it's a proportional controller, because you have that the control input is proportional to the error, is k times e of s. All right, so with these assumptions, let's rewrite the closed loop system. Now, instead of g of c, we simply have k, and we can substitute g of s with the expression that we already had. And now the question is the closed loop system stable? Because we don't know really. By closing the loop, even if you started with the stable system as it was, because it had poles at -1, -2, -3, and -4, by closing the loop, if you remember, the poles, we did it for a second order system, the poles travel away from their original location. So here we have 4 poles that we start from. So how do they travel in the S-plane? Can they go in the right-hand side of the plane for some values of k? It might be. If that is the case, well, that's a problem. We don't want the system to become unstable. So we need to design the value of k so that the system is not unstable. So we have a few ways to do so in order to find the stability of the closed loop system. Well, we can use what we've just developed, that is the Routh-Hurwitz criterion. And so in order to do that, we need to work on the characteristic equations, and that's what we're going to do now. Or you can use just brute force and compute the poles of the closed loop transfer function. But again, here we have 4 of them, and it's not possible doing it by hand, or it's very inconvenient. It is still possible, but it's going to be very long. And then the third option would be to use what it's called the root locus method. So it'll give you all the possible closed loop poles for all values of the parameter k. So this is very powerful, and we're going to talk about it later. But now we're only familiar with case A and B. So let's use the Routh-Hurwitz criterion to check the stability, to assess the stability of this closed loop system. So we need to find the closed loop transfer function. So for the system, we have k times gs over 1 plus k times gs. Or I'm writing all steps. Now we can multiply numerator and denominator by s plus 1, s plus 2, s plus 3, s plus 4. And so we find k. And be careful here when you do that, because there are always, I always see mistakes. So be careful with your math skills. I've already done this earlier, so I can go a little bit faster. But when you do it, try not to skip steps, because you're going to make mistakes. That's always when you make mistakes, is when you are extra confident in your math skills. You'll always forget something. So just go a little bit more slowly and make sure that everything is properly done. Again, here I've already done it, so I can go a little bit faster, also because we don't really have all the time in the world. But anyway, finally, we have our transfer function written as a numerator over a denominator. So having the denominator, well, this is the characteristic polynomial. Or delta of s. Well, we have the characteristic polynomial. Why don't we construct the Routh array? All right, let's use the coefficients. We have 1, 10, 35, 50, and 24 plus k. Now, first term of the third row, we have 10 times 35 minus 1 times 50 divided by 10. It's going to be 30. And then for this term here, we want these and these. Here we have 0, so it becomes simply 24 plus k. And then we have over here this term. We need these 4 coefficients. So this is always using the figure 8, 30 times 50 minus 10 times 24 plus k, everything divided by 30. And this is going to be 42 minus k over 3. And we have 0 here, and so the last one is 24 plus k. So now the Routh array is the following. 1, 10, 30, 42 minus k over 3, and 24 plus k. Again, our objective is to find a range of k, so a controller, that keeps the system stable. So we want all the coefficients of the Routh array to have the same sign. Since we have plus 1, plus 10, plus 30, then we want 42 minus k over 3 to also be positive, and 24 plus k to be positive as well. Since we've conjectured that k is positive, well, 24 plus k is always positive. Here you would have k greater than minus 24, which is checked. But from the first one, from this inequality, you'll find that if we multiply everything by 3, we have 126 minus k greater than 0, which implies that k has to be less than 126. So the range for stability is that k must be between 0 and 126. So if you have any value of k between 0 and 126 excluded, then your closed loop poles will all lie on the left-hand side of the S-plane. Where are they exactly? We don't really know. They might be right here, or they might be a little bit in other locations. We don't know. They might all be real. We don't know that yet. So, and that's why we're gonna develop the methodology known as the root locus to find exactly all the possible locations. So we're gonna find some lines that represent all the possible locations of the closed loop poles as we change a parameter, that is k. The alternative would be just, you select a value of k and then compute the poles of T of S. Going back to the characteristic polynomial, let's say you pick k equals 1, and then you have all the characteristic polynomial with the constant term equals to 24 plus 1, that is 25, and then you compute the closed loop poles and check the real parts. And then you have to change the value of k, maybe 1.5, but you have an infinite amount of values of k, so it's really impractical. The Routh array doesn't tell you where the poles are, it just tells you the range of k's for which the system is stable. So it gives us good and useful information. However, the root locus method will give you all the possible solutions as k varies. All the possible solutions for the closed loop poles of the transfer function. All we know now is that as we pass k equal, if k is greater than 126, the system will become unstable. So intuitively, for k equals 126, you're going to have poles on the imaginary axis. You have the transition between a stable system to an unstable system. And at that transition, the system is marginally stable. But we're going to see the root locus next time. So for now, this is all, and take care.